This is one of the most famous photographs in astronomy, the so-called Pillars of Creation. These vast clouds of gas and dust are in the Eagle Nebula.
Pillars of Creation is an apt name. Nebulae play a key role in the life cycle of stars. They're there at their birth and at their death. And so tonight, The Sky at Night investigates what makes these delicate clouds the crucibles of creation. Today we've come to the University of London Observatory, where scientists have watched many of the magnificent processes that sculpt nebulae.
Despite being beside a noisy and rather well-lit A1, some of the most dramatic nebula can be seen from right here.
Coming up, what triggers these spectacular clouds to collapse and give birth to new stars?
And how the process turns full circle as dying stars create new nebulae.
Plus, Andrea Sella reveals the surprising chemistry that takes place inside these interstellar clouds, creating ingredients for new stars.
For me as a chemist, the idea of chemical reactions happening in this environment seems almost impossible. But that turns out not to be the case at all.
And Peter's here with his guide to the best nebulae to see this month and how to photograph them.
So let's take a closer look at that image that we saw just a few minutes ago, the magnificent Pillars of Creation. The image is from 1995, taken with the Hubble Space Telescope, and it's a mosaic which accounts for the strange jagged shape. But what you should really concentrate on are the magnificent structures that it reveals.
I think this picture really captures people's imagination because it's what we expect to see out there in the heavens. Wondrous beauty on a really epic scale. And it truly is epic. Those tiny finger-like protrusions on the top of the columns are in fact larger than the whole of our solar system. But in the beauty, there is also science. These vast columns of dust and gas, known as elephant trunks, are the home of star formation. And it just goes to show the vital role that nebulae play in the life cycle of stars.
This is a process that happens in nebulae all over the universe. But we can see it in action here because of the way the nebula is lit. The Eagle Nebula, which forms the backdrop to the pillars, is an emission nebula, which means the light comes from hot, glowing gas. And the different colours that you can see represent emission from different elements in the nebula. But the real action here is in the pillars themselves. And to take a look at that, we need to switch to the infrared. And in this image from the Herschel Observatory, that's exactly what you can see, the cold gas and dust in the pillars ready to collapse and form stars.
Although we know that stars are born in nebulae, the details of that process remain a mystery.
But what is becoming clear is that one key factor is the extraordinary chemistry that takes place, reactions that simply shouldn't be happening.
Chemist Andrea Sella is finding out more about why chemical reactions are so unexpected in space and what role this remarkable chemistry plays in star formation.
As a chemist, I see my field as the study of matter and the way in which it can be transformed. We look at the way atoms come together to form molecules and the way in which those molecules interact. But chemical reactions usually need certain conditions in order to take place. Conditions that are common here on Earth, but not in space. I've set up some experiments here in the lab to demonstrate some of these factors. So the first key factor is actually temperature. And I'm going to illustrate this with these two colorless solutions that I'm going to mix together at room temperature. And when I do that, you can see that actually not very much happens. But if in fact I move this onto a hot plate, the molecules, because they're getting hotter, they start to move faster, they collide more violently, and the result is they're more likely to react. And look, it's already gone. If, on the other hand, we actually took this reaction and put it on ice, then everything would become really sluggish and slow, and the reaction would take much longer.
The trouble is, heat is a rare commodity out in deep space, where the temperature is close to absolute zero. And temperature isn't the only consideration.
So the second factor that controls a chemical reaction is actually the concentration. In other words, how many molecules we actually pack into a given volume of our solution. Now, I've got exactly the same setup we had before, but what I've done is I've actually increased one of the concentrations. And when I mix them together, the reaction goes instantaneously.
So having molecules crammed in close together makes these collisions much more likely. And this presents a real problem in the emptiness of space, where the chance of one atom encountering another is infinitesimally small.
Even in a nebula, the material is so spread out, so diffuse, that if we imagine one atom to be the size of this penny in London, the next atom is way off, somewhere in Manchester.
And there's something else we can take advantage of in the lab. We can add a catalyst to encourage a reaction.
So in this flask, I've got some methanol, an alcohol, along with, of course, oxygen from the air. And there isn't really very much going on. But if I take a little bit of this platinum wire and I place it inside the flask, then something interesting is going to happen. Now, before we put the platinum in, the methanol and the oxygen weren't reacting. But now that the platinum is actually in there, the methanol lands on the surface, the oxygen lands on the surface, and they start to react. And notice that what this does is it raises the temperature. The platinum is beginning to glow, and the reaction is going faster and faster until eventually it all gets so hot, the vapor itself ignites, and it goes pop.
But none of these phenomena we find in the lab are the kinds of things we'd expect to find in deep space.
So for me as a chemist, the idea of chemical reactions happening in this environment seems almost impossible. But that turns out not to be the case at all.
Scientists know that there are in fact many complex chemical reactions taking place within nebulae, despite the seemingly hopeless conditions. Not only that, they're a crucial part of the process by which stars and planets are formed.
The thing which I think is funny are the echoes.
Cosmochemist Steve Price attempts to recreate these reactions in a vacuum chamber, right here in his lab.
So Steve, what's the evidence for the idea that there's chemistry actually in nebulae?
Well, we can actually see the molecules by observing the light that they emit. We can actually see that, from the atoms that we've got to start with, we must be doing chemistry to make molecules like molecular hydrogen.
But making hydrogen, I mean, surely that's trivial. It's just taking two hydrogen atoms and combining them together to make an H2 molecule. I mean, isn't that the simplest thing you can... Why is that interesting?
Because you think about doing the chemistry on Earth, where it is very easy. But in nebula, we've got very low pressures, so the H atoms don't encounter each other very often at all. And it's very cold, so they don't hit each other very hard. But also, they can fall apart very easily. We need something to actually bring the H atoms together to help them react and actually form that H2 molecule.
Luckily, nebulae aren't just vast clouds of gas. They're also full of microscopic dust particles. And it's these dust particles that are key to forming new molecules.
So what's the role of these dust grains?
Well, the dust grains allow us to bring the atoms of hydrogen together to form H2. The atoms stick on the surface of the dust grains, they run around and find each other, and that enables them to form H2 much more efficiently than they would out in the gas phase.
So you're really talking about a catalyst. I mean, a bit like the platinum surface that we saw earlier.
Exactly like that. Yeah, without the dust rain, the atoms wouldn't really encounter each other for long enough to make H2. So it's vital in bringing them together and making the reaction happen. So yeah, it's a catalyst.
And so what do they look like?
We think the dust is rough, and here's a picture of some simulated dust grains that people have made in the laboratory, and you can see they're nothing like your nice flat plateau
horrible.
Of carbon. Oh, I think they look
It
quite
looks
pretty.
like cauliflower.
But what you can see straight away is it's sort of textured and fluffy surface is actually perhaps important for trapping molecules on the surface and various other things. So the structure of the dust is really quite important.
Now, we've talked about the formation of hydrogen molecules, but what other things are out there? What other molecular species are there?
There's an enormous number. We're almost, I think, up to 200 other species we've seen out there of these interstellar molecules. A huge range of things, your long carbon chains, things like methanol, ethanol, and trying to explain how you form these very complicated molecules in these very extreme conditions of low temperatures, low pressures where you don't collide very often has been a real challenge. And a lot of the molecules are formed by unusual gas phase chemistry, but for many of them, water, methanol, we also need to say that things are being formed on the dust grain surfaces as well.
So why are molecules so important inside nebulae?
One of the things that these dust clouds in the nebula do is they collapse, and in the end they form stars. But for that collapse, actually, we need to lose energy from the molecules to actually slow them down, to let them collapse. And you need molecules to do that. The molecules get energized in collisions, but then emit light, and that light then goes away from the nebula, and you've lost some energy. So it allows the cloud to collapse and cool. So chemistry is vital in making the molecules, which are vital in forming the stars.
And so chemistry really lies at the heart of star formation.
Yeah, we couldn't form stars without the molecules, and we need chemistry to form the molecules, absolutely.
Nebulae provide the perfect environment for star formation, but the processes that trigger this formation are shrouded in mystery. Chris is investigating the inner workings of nebulae with star formation expert Serena Vitti.
I always love talking about star formation because it's a problem that gets more complicated the more you know about it. The basics are understood. We've got to get something to collapse, but we don't understand the detail of how that happens. So what do we know? Do we know where stars form, for example?
Yes, we do know the stars form from dark molecular clouds.
And we've got a picture of one of those cores here. So what are we seeing here?
So that's right. So this is Barnard 68, and it's a dark core, very cold, about 10 Kelvin or minus 250 degrees Celsius or something like that. And it's about a third of a light year across. And this core may start forming a star because of gravity. So gravity will take over and collapse will happen.
And so it's important that it's dark because that allows it to be cool.
That's right.
It seems strange to be talking about the temperature affecting gravity.
Basically, if a gas is not cold, then the atoms and molecules in this gas will start moving faster and faster as the temperature increases. And if they move faster and faster, then gravity cannot take over and the gas cannot collapse.
Okay, so that's why the molecules are important then.
Yes, because the molecules allow the gas to cool. So molecules radiate away the heat from the cloud, and the temperature will be low enough for gravity to take over. And you have a runaway effect. And eventually, right in the center of this core, you will have a very dense and very hot core, which we call the protostar.
I think we've got one of these here.
That's
Yep,
right.
here we
So
go.
this is L1157. This is an infrared image from the Spitzer Satellite Telescope. This blob of gas is very hot, and nuclear fusion will have started. And due to the high pressure in this core, you start seeing these jets of gas coming out.
We've got an image here from Herschel. So what are we looking at here?
So these are filaments of gas and dust, and you can see the stars forming inside the filaments. And what this is telling you is that stars don't necessarily form from round, well-defined cores.
What does that mean? What does that tell us about the process?
Well, it tells us that the giant molecular clouds, when they fragment, they can fragment in different forms, filaments course, and that's all to do probably with turbulence, but we still yet don't know where this turbulence come from in the first place.
But something stirred them up.
Something stirred them up, yes.
Interesting. And what are the big unknowns in this field? Like, what don't we know about star formation?
Well, we certainly don't know where turbulence come from, for a start. We also don't know how the most massive stars, so stars much larger than our sun, how they actually form, because the process of star formation there is not so well understood, because due to the initial mass of the cloud, the collapse must happen very quickly.
Just because gravity
Just
is more
because
important,
gravity,
you've got more stuff.
That's right. With the spect, when you have so much mass, the stars falling, then the heat would be so high, the pressure should kickstart basically equilibrium. You should stop gravity to
So you quickly reach a stage where you can have a protostar and all of this other stuff, but
before you build up mass in the center to get to these massive stars, and yet we know that these massive stars exist. So there are several theories out there on how these massive stars can form, but the jury's still out there.
Interesting. Well, come back and tell us when you find out.
You might think that to capture astonishing images of nebulae, you need a multi-billion-dollar space telescope. But that is definitely not the case at all.
Yeah, this is just a...
Pete's gone to meet members of the Newbury Astronomical Society to see what they've photographed from right here on Earth.
Ah, that's beautiful.
Yeah, M27, the Dumbbell Nebula.
Oh, yeah.
This is taken from 4 45-second subframes.
The subframe is a fancy way of saying the exposure, one exposure.
Yeah.
That's a pretty good job, though, I have to say. There's lots and lots of beautiful detail in there. And you can there's a little threesome of stars there right in the centre. And yeah, and if you can split those, that's supposed to be the mark of a good dumbbell. So,
thank you very much.
So well done.
I'll take credit for that.
Thank you very much.
Thanks, Pete.
John, I think you've got one of them. There it is, the more exotic nebulae in the winter skies.
Yeah, N1, Crab Nebula.
That's a brilliant picture.
Well, actually, it's my first attempt at what we call an LRGB image, taken with a black and white camera through a red filter, green filter, blue filter.
Well, it's worked really well because you've got that lovely colour in the background, but you've also pulled out all the filaments which are there, and
well, it literally looks like an exploded star, doesn't
which
it?
is exactly what it is. It's a supernova remnant, and one of the stars in the centre there is the pulsar, the neutron star, which drives it. It's one of those pair, and for the life of me, I can't remember which one it is. Yeah. I remember looking at this when I was at university, actually. We looked at various pictures of it taken many years apart, and you can see the expansion of the gas.
Yes.
So there's another record which you could put against that and see how much it's grown. Yeah. Isn't that incredible?
Perhaps I'll take another one in 10 years' time.
That's a brilliant result. Well done.
So how can you go about imaging nebulae too? I've got some simple tips, starting with where to view them from.
Nebulae are fantastic objects to look at, but unlike stars, which are point objects in the night sky, nebulae are diffuse, and to get the best possible views of them, you need to get to a site which is really, really dark and doesn't suffer from too much light pollution.
You can get a surprisingly good view through a pair of binoculars or a telescope. And one of the best to start with is the Orion Nebula because it's so bright.
Now, when you think of an image of a nebula, you probably think of something which is bright and colourful. But actually, when you look at one of these objects through the eyepiece of a telescope, what you'll see is something rather grey and smudge-like. But the longer you look, the more detail you'll see. And when you look at a bright nebula, like, for example, the Orion Nebula, you can actually start to make out some colour. It's possible to see, for example, a greenish hue to it. Now, that's given off by oxygen atoms, which are excited, and they give off a wavelength which is in the most sensitive part of the visual range of our eyes.
But to see the colours of nebulae in all their glory, you need to turn to a camera.
Now, the best way to get a nice image of a nebula is to take a long exposure photograph. But if you're using a fixed platform like this tripod, the problem you've got is if you take a long exposure, the Earth's rotation tends to make the nebula trail.
A simple solution is to use a wide-angle lens, taking a short 30 to 60 second exposure. This should capture the nebula as a small coloured patch. But to see real detail, you'll need a telescope, and for that, a tracking mount is essential.
For details of some great nebula to look out for, here's my guide to what's up in this month's night sky.
The Orion Nebula, M42, is big and bright and can be seen with binoculars sitting right at the centre of Orion's sword. Above M42 is NGC 1977, the Running Man Nebula, so called because long exposures of it show the silhouette of a running figure. The famous Horsehead Nebula hangs down from Alnitak, the eastern star in Orion's belt. A large telescope is required to see it, but the nebula can be picked out with modest imaging kit. The Flame Nebula, NGC 2024, also lies just east of Alnitak. The Pleiades Open Cluster is high in the sky before midnight during December. North of the Pleiades is NGC 1499, the California Nebula, a deep red emission nebula in the constellation Perseus, and it's quite spectacular.
We talked about how the clouds of gas and dust that make up nebulae can collapse to form new stars. But where did that material come from in the first place? Surprisingly, the answer is from other long-dead stars. When high-mass stars reach the end of their lives, they explode in an astonishing display that we call a supernova, and the debris that's left from these explosions becomes a type of nebula. Maggie is talking to Steve Fossey, who uses the telescopes here to find and to study these phenomena.
On a cloudy day earlier this year, Steve and some of his students made an astonishing discovery. During a brief break in the clouds, they imaged M82, the Cigar Galaxy. And immediately it was clear that something was different.
We took our image on January the 21st.
And that's this image.
And that's this one here. Now this is a shorter exposure and under some cloudy sky, so it's a bit grainy. But you can see there's a new object.
So this one here?
That's right, on the bar of the galaxy that clearly wasn't there before. And I said to the students, well, this is very unusual. This potentially could be a supernova.
It was a supernova. And soon it became clear it was a very special kind of supernova.
By 6 a.m. the next morning, the spectrum, which had been taken by a professional group at Palomar in California using a telescope system in Arizona, they'd confirmed that it was a supernova. And in fact, not just any old supernova, it was what we call a thermonuclear or a type 1a supernova.
Because they're quite rare.
Those type are rare. We think, on average, a supernova in a typical galaxy like the Milky Way, on average about once every 100 years. Ooh. Those type about twice a millennium.
Oh, wow.
In any given galaxy.
So now the supernova has exploded. So what was left behind? Because sometimes you get black holes, sometimes you get neutron stars. What was left behind with this one?
Well, this type of explosion comes from something that we call a white dwarf. It's about the mass of the sun, but about the size of the Earth, and it's the dead core of the star that was. And if this is in a binary star system, it can draw gas from the binary partner until it reaches a critical limit at which the temperature in the core rises to several 100 million degrees. The carbon atoms fuse together in a runaway thermonuclear explosion that blows the whole star apart in just a few seconds, and there is nothing left behind.
So what happens to the envelope that's expanding outwards?
So we have an expanding envelope of hot gas, the outer layers of which are moving at, say, about a 20th of the speed of light. So very, very rapid expansion. A hot bubble of gas. And we see these kinds of objects within our own galaxy. So in this example here, we have a supernova remnant. And this is the remains of actually a much more massive star which exploded, we think about 30,000 years ago. And that shockwave has picked up hydrogen gas and other elements and swept them up into thin filaments to create this rather shell-like structure.
So will your supernova look like this, given time?
Well, eventually some of the gases from the explosion will probably hit some of the surrounding circumstellar or interstellar material. We will never see it like this because it's so far away. What it may well do is it may well glow in the radio part of the spectrum because it picks up electrons and they move so fast that they radiate energy in the radio part of the spectrum. Most of the supernova remnants in our galaxy have been discovered through radio observations.
So the gas continues moving out. Does it just continue doing that until it sort of disintegrates?
Exactly. Eventually it will dissipate over some tens of thousands of years. So actually this is a process that has been going on in the Milky Way for billions of years. Supernova remnants which have come and gone. I think of the Milky Way as like a giant recycling unit. And so supernovae like the one in Messier 82 will produce new elements and dust grains as well, which are so important for new star formation. So this supernova remnant compresses the clouds and it stirs up the interstellar gas, creating turbulence, which then leads to the formation of new and complex filaments within those clouds from which new stars.
So it provides the pressure for the star formation to start.
Exactly. It provides the pressure in the interstellar gas to trigger new star formation.
Well, that's fantastic. Thank you so much, Steve. It's been brilliant.
We couldn't let this episode pass without updating you on the status of Philae, everyone's favourite comet-bouncing lander. It's still dormant on the surface of Comet Churyumov-Gerasimenko, but we have had some exciting news here on the ground.
Firstly, the search for Philae on the comet's surface continues. ROMAP, the magnetometer on board Philae, has got some more information, which has indicated that after the first bounce, the second bounce caused Philae to actually drag one of its feet in the surface, and then it's caused it to tumble. Now, we've also got an image of where we think the lander is likely to be. And we've got two potential landing sites. We've got that long strip there, and also the green spot. Now, we think that it might have been in either of these positions, but it very much depends on the topography of the surface.
And so in either case, it is where we thought it was, on the edge of this crater-like feature. But we found a new way of visualizing this. So this is the first image that we got from the surface. There's the legs sitting down and these bouldery crater walls in the background. But an image processing expert called Matthias Melmer has processed this image, made a guess as to the distances, and created this visualization. So don't be distracted by the colors, they're exaggerated. But I think this gives you a real sense of depth, and you get the sense of Philae clinging on the edge of a cliff. And if you look at that and then go back to the original image, I think you understand where it is, on the edge of this quite precarious pit.
Yeah, it looks like a pretty craggy surface, doesn't it?
It does.
Speaking of the surface, both Ptolemy and Cossack, the onboard chemical analyzers on the Philae, have detected organic molecules. This is really exciting. We sort of expected to see something there, but I'm really looking forward to find out exactly what they are. And finally, given the time of year, we couldn't end the programme without a look at this. The very festive Christmas tree cluster, set against the background of an emission nebula.
That's it for this month, but when we come back next month, we'll be investigating Gaia, the remarkable mission that's set to transform our view of the Milky Way galaxy.
We'll be looking at the billion-pixel sensor at the heart of this mission and discovering how your images can help verify its results. So in the meantime, get outside and get looking up.
Good night.
A tribute to some legends of British and international rock here on BBC4 Next tonight. Stay with us for both parts of the epic profile Days of Our Lives. Queen back to back in just a moment. And then at midnight, air guitars at the ready. It's time to rock out with some great American anthems. Don't go away.